You
Okay,
too.
so today we're going over graphs. Yes. So yesterday we went, I mean, not yesterday, last week we went over queues and I can see it. Can you put it in present mode?
Yeah.
Nate, thanks. So last week we went over queues and stacks. That was kind of an important topic. You don't need to know it right now because I don't think we'll get to the queue part, but next week we definitely will. So next week we're gonna go over like another one of those super important graph algorithms that shows up in interviews all the time. So if you want to familiarize with yourself with stacks and queues, you can watch my video on YouTube. Okay, could you go to the next slide, Nate? All right, so I have this class, it's called the religions. It's the religions class. And you know, when she started, the first slide was, what the heck are religions? So I took a page out of her book, What the Heck Are Graphs? So just read. They're like not that complicated. So there's just a bunch of vertices that are connected with little lines, and you can traverse across these lines, and path can be like, that's called an edge, those lines. And could you go to the next slide, Nathaniel? It has a visualization. Yeah, that's a graph, you see. So it's just a bunch of, like those red dots are vertices or nodes, and those little lines are called edges. Now in this case, this is called a directed graph, which means that if you have like, you can have connection from only one side or both sides, but like if you want a connection on both sides, then you need to have two different edges. That's important. Can you go back, Nate? Whoa, spoilers! uh,
My bad.
no problem. Kidding. So the graph is called, well, okay, path. Let's start with a path. A path is a single edge or more than one edges. Basically, it's just a path from one node to another node. Think of Orlando to Miami. There may or may not be a direct road between Orlando and Miami, but there is definitely a path. So yeah, like for example, think of UCF to, I don't know, pick your favorite Chick-fil-A. That is not on UCF. You probably have to take a few turns here or there. Like those like intersections, they're probably, you can consider those as nodes. So you keep having to switch edges or like lines in order to get somewhere. So there is a path from UCF to your second favorite Chick-fil-A, for favorite being the one on campus. But it's just, it involves more than one edge. A graph is called connected if there's a path from any node to any other node in the graph. The world is not connected by road. That is why you cannot drive from North America to Europe. Actually, probably can, because like Alaska, land bridge. I mean, I don't know, whatever, you get my point. And then the individually connected parts of the graph are called its components. So Nate, could you go to the next slide? Yeah, so those are like, for example, if you look at the node 3, it's connected to 5 and 1. So that's technically a component. I probably picked a bad example, but what I'm trying to say is like, if a component is connected, you can, in a subconnected component, you can find a path from any node to any other node as part of the component. You cannot do that from 3, 5, 1, because once you go to 5 from 3, you cannot go back to 3 from 5. You have to go, I don't think there is a path. So, okay, this isn't even like a fully connected graph.
Is this just a picture of this graph or all graphs?
Huh?
Is this just like the one direction like path of it? Is that just a feature of this graph or of like all graphs?
It's a kind of graph. It's called a directed graph, which means that the edges in this graph are one directional. If you want bidirectional edges, you need to have two different edges. One going from 3 to 5 and another coming from 5 to 3. Does that make sense, Nate?
Yeah, that makes sense. Thanks.
Okay. Also, is Andrew back? Andrew, you left me.
Oh, sorry. I had a power out surge.
Oh.
That lasted like literally a second.
I still blame you.
It's the worst luck.
Okay.
Fortunately, my neighborhood gets frequent power out surges. Don't know why.
That's not fortunate. That's unfortunate.
I don't know. I just blame Duke.
Yeah, blame Duke. Okay, anyway, could you go to the next, well, all right, for the Andrew's benefit, can you go back to the last slide? Andrew, screenshot this and read it on your own time.
Cool.
It's not that much. It's just like a graph is a bunch of nodes and vertices connected with edges. And that's all you need to really know. Like the rest you'll kind of pick up with context.
Okay.
And on the image on the next slide is an example of a graph. All right, so now that we know what graphs are, let's talk about representations. Now, this isn't a slide. I did not include this as a slide. I'm hoping that my screen share will work this time, but if it doesn't, I'm going to send out a REPL link. Is that okay?
Are you asking me? Yeah, I can do that.
All right, cool. So the first thing, like I'm gonna try sharing my screen here. All right, so this is just like live coding everything, so don't laugh at me. I actually made a problem for you guys. I wrote a problem myself. But here, I can't spell today. So there's 3 ways to represent a graph. Really, this should have been a text file rather than like a normal file, a class, a Java class. But we'll just pretend that I know what I'm doing here. So the first one is an adjacency matrix. Now, this can be a matrix of anything, really. It could be a matrix of Booleans. It could be a matrix of integers, of strings, anything that can convey information like to you, to tell you that there's a path between this and this. So I actually use this method, but really let's just say that there's this graph A, B, okay? And there's only 2 nodes in this graph, and also let's just make it like undirected. So it's connected both ways, or rather there is no direction, which means that it's connected both ways. So how you would represent this in an adjacency matrix is a list of lists. Oh no. Okay, so the first one represents A, the second one represents B. Is there a connection between A and A? Technically, yes, but we're not going to go down that rabbit hole, so we're going to just say it's false. So let me make this a bit clearer for you guys. Here's
Arjun,
A.
Are you typing on the screen right now?
It froze again.
Yeah.
Aha, this is why I didn't rely on it the first time. Okay, Christopher asked too. Sorry, Christopher, you're gonna have to speak up. Unmute yourself.
My bad, sorry about that.
I don't really read chat that much. Nate, let me send you out a REPL link.
Gotcha.
I actually need to figure this out because this is getting annoying.
Yo.
I tried uninstalling and reinstalling Zoom.
Do you have like a security setting maybe?
No, that's not it. I think it's just Big Sur, Mac OS, the new one. It just like really messes with. Okay, I'm gonna keep this PG friendly because it's being recorded, but it really messes with the Zoom screen share sessions. I looked it up. I can, like, for the people who have Macs like me, right. So for the people who have Macs like me, it's kind of a pain. But anyway, Nate, can you go to that REPL link? Yep, there we go.
Oh, can you see my screen?
No.
Oh, okay. You said there you go, and I was like, huh? Okay, I see. Trying to find the window. There it is.
Awesome.
Do you see it?
Go to go to graph representations. Just refresh. There you go. Go to graph representation. Now I'm gonna live type here. I wish all of you had VS Code so then we could just live share, but I can't assume that's true. So we'll just go with this. So here's a very simple graph. A and B are the two nodes, and there's this like little edge in between them. What we're doing here is we've created this little table, and it stands for it's just basically saying like this is what it is. You know, like you've seen those pairings charts, right? Like when you're in a tournament and like this person against this person against this person. I'm gonna assume you have. So it's like that. So what this is representing is that between A and A, there is no path, so that's the false. Between A and B, there is a path, that's why it's true. Between B and A, there is a path that's true, and then between B and B, there is no path, which is false. The only reason that I didn't put a true between A and B, even though like, yes, there is a way you can get from A to A by just staying put, is because then we get down a rabbit hole sometimes, and it can get confusing for people. Does this make sense, adjacency matrix? We can probably expand it a little more if you guys want. Let's say that there were 3 nodes now, for example. So there'd be a C node here. And there is no direct path. There is a direct path from A to C, that's why there's a true here. And there is no direct path from B to C, which is why there's a false here. And we also have to do a representation of C. So there is a path between C and A, so that's why it's true. No path between C and B, and then no path between C and C. If this makes sense, I can move on. Unmute yourself, please, and just tell me, because we have a lot to get through.
Makes sense.
Yeah, makes sense.
Okay.
Yeah.
Okay, awesome. All right, so the next one is an adjacency list. Oh, by the way, you can represent this with, like, for example, for the adjacency matrix, you can represent them with integers instead of booleans. So like, if it was like an unweighted graph, which means there is like the cost to travel from one edge to another edge is the same, then if the edge exists, you can just say 1 and 0. But if there's like different costs between traveling to edges, you can represent that with an integer or a double or a float or anything really. And if like each node has a string that is an identity, then you can do object-oriented programming stuff for that one, make a class node. I think, yeah, one of these days I really need to do a lecture on object-oriented programming. But remind me to do that sometime. Any one of you, I'm reachable on the Nighthacks Discord. All right, so adjacency matrix, adjacency list. Now this one is kind of similar, where for the same graph, you'll just say, okay, there's a path from A to B and C. There's a path from B to A, that's all. And there's a path from, God damn it. And then there's a path from C to A, and that's all. This is an adjacency list. It's just saying like for each node, it just lists the neighbors out. Make sense?
Makes sense.
Yeah.
Yeah.
Awesome. All right, the last one is an edge list. Now this one's a little different. So here, let us define a way of like storing an edge. Anyone, any people familiar with C++?
Slightly, but not a whole lot of experience.
That's fine. Okay, so C++ was a data type called vector, or okay, well, fine. Python?
Yeah.
All right, so do you know tuples in Python?
Yeah, a little bit.
Yeah. So there's like, you can just consider it that way. An edge list is just a list of all the edges. So there's an edge between A and B. There's an edge between B and A. There's an edge between A and C. There's an edge between C and A. And if this was undirected, we could just take two of these out because an edge between A and B implies an edge between B and A. And then there's an edge between, that's all actually. So I have a pop quiz for you guys. Is this graph that we're currently looking at, is that a fully connected graph? Now, review a definition here. A fully connected graph means that you can go from any edge to any other edge.
Yeah,
Why is it fully connected, Nate?
because you
Is
can
it cool
go.
if I call you Nate?
Yeah, that's fine. I go by either. Because you can go from like C to B by going through A.
Awesome, awesome. And works the other way as well, B to C as well. Okay, great. So you got that. All right. So now, can you jump back to the presentation? So graph traversal algorithms, this is an empty slide. I meant to fill it, but I spent most of the time preparing for this session by writing the problem. So please skip that slide. All right, so this is depth first search, DFS. I probably should have written depth first search. The bottom line for this algorithm is that you should be Alice. Anyone, if you're familiar with Alice in Wonderland?
Yes.
So you want us to
Yes.
go down the rabbit hole?
Yes, yes, thank you, thank you. This
Okay.
should be called the rabbit hole algorithm. So could you click that link, the YouTube link? Just go to that. I should have hyperlinked it. Ah! All right, so this is an example of an animation that does depth first search. It took me a really long time to find this one because everything else was just people explaining the animation. I want to explain it. I just want an animation that accompanies me, and this is good. So this person is a genius, and he made this thing. So yeah, he randomizes the path and just till like there's your node A0 that has a path, at least one path. And then he starts the depth first search. So you see that the first, like pause, could you pause, Nate? So you see that when you start at A0, the first edge he goes along is the first one he sees, which is B0. He travels that and he goes to B0 and he sees that there's nothing else, nowhere that he can go to from B0. So he goes back to A0, kind of backtracking. And then he goes to the second edge he sees, B1. So he travels along B1. Then the first edge that he sees from B1 is B2. So he goes along that one. Then from B2, he sees the first edge is B3. He could have taken A3 or A2, but he doesn't. He takes B3, and that's the first edge. And continue, could you unpause? Yes. And he continues going down the rabbit hole. You see why this algorithm should be called the rabbit hole algorithm? Does this make sense?
Yeah.
Everyone other than Nate?
Yeah.
I think so.
Wait, why was it that he took from B2 to B3 first?
I think it's just whatever edge you see first. It doesn't matter what edge
Oh,
you see
okay.
first.
Gotcha.
Okay.
So it wouldn't have to do with like weight or anything like that of the edge.
No, no, we're not getting to that yet.
Okay.
Oh man, there's a ton of things we can do with graphs, really, and like we haven't even. I'm afraid we won't even be able to live code up DFS in today's session. So I'm going to spend a long time on graphs. All right, let's go to back to the slides, Nate. All right, so that's DFS. Do you guys understand like the high level approach to the algorithm?
Yeah.
Yes.
Yeah, I mean,
Okay.
it's like reminds me of backtracking from CS1 anyway.
It is backtracking from CS1
Yeah. So
because you're going back to the initial node. It's
Right.
really easy, actually. It's the easiest graph algorithm, and it's so useful. All right, let's go to the next one. All right, so in breadth first search, you're a little bit smarter. Emphasis on little bit. So first thing you do is that you remember queues, right? Like from the previous session.
yeah.
Christopher, Leia, Andrew.
Yes.
I know of them. I wasn't here last time, but I know about queues.
Yeah, this is my first session actually.
Yeah, I know, Leia. You should come more often. Anyway, Andrew, do you remember?
Repeat that again.
Do you remember what a queue is?
A queue is in a line, so I think it goes first in, first out.
Exactly. Andrew got it. You're on top of it, man. Anyway, so in BFS, which is breadth first search, contrast that with depth first search. I don't have a funny nickname for this algorithm. We can call depth first search Alice, but we can't call breadth first search Alice. Help me think of one, and like I'll continue with the session, and then later we can vote for which one is the best nickname. Anyway, so you start out at your current node. You can start out at any random node actually, but let's just start at node 1. And then you NQ all the nodes that you see. So like all edges that you're connected to, or all nodes that you're connected to through this node, through edges. You put them in a list or a line or a queue. And then you go through the first edge in your queue and you remove that edge from your queue. Go to that, and then like you repeat step 1, which is you're at a different node. Then that different node has more edges. You kind of like list them in your queue again. Now, keep in mind that right now that your queue has like a few edges that the original node had, and now it has the new edges that this node that you've just come to has. And then you repeat step 2. And once you've finished like the whole process, recursive process, that means you've traveled all edges. The print hello world was just a pun to see how any of you were actually reading. Are you reading?
So are you not supposed to print hello world, or?
I mean, you're supposed to print out hello world in every algorithm, right?
That's what I thought.
Yeah. Anyway, could you go to that video? This one's a bit longer, but it's kind of important. Also, we're gonna watch your YouTube recommendations.
Yeah, I noticed that last time. Hang on. Sorry about that. Okay.
You can go on to like incognito mode or sign out or something.
That's like too
You're a
much
total,
effort.
yeah, you're a total nerd though. It's good. Nerds are fun. Nerds are awesome. I respect that.
I'll just say.
This
Or do
one
you just
has
want
a
me to play it, or?
disgusting yeah, yeah. This one has a disgusting music though. Oh, there's no music?
Good
Never
thing we
mind.
can't hear it then.
Oh, I just hear the music then.
Oh, that's good. You deserve it. Anyway, could you pause for a second? So it's kind of hard to see, but do you see those like little lines between those edges or between the nodes?
The lines.
Yeah, there's a little few lines between the nodes.
You talking about the green ones?
Yeah.
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 You can see them? Good.
Yeah.
Those are edges, right? So you'll notice that there is no connection between any node to any other node, like no edge between any node to any other node. It's not like you can travel from node 0 to node 25 in just one edge, but like you can somehow travel to it through like, you know, going along multiple edges. Could you play that again? I mean, could you unpause? All right, so what it does is that it dequeues the first vertex from the queue of vertexes or edges that it has to travel. Then it travels along those things. Yeah, so you see Now it's connected all four, like, and queued them. Then it goes to the first one, then queues all of them. So 6 has like 11, 12, 13. Those edges or nodes are queued. But like it's going kind of in order. Does that make sense?
Yeah. Them numbering it helps a lot. So you know which one they're gonna go to next.
Right. So now it went to 11, queued 17 at the back. Then went to 12. 12 has no connection, so that's it. Then it goes to 13. 13 has no connections. 14 has no connections. 15 has no connections. 16 has no connections. 17 has one connection. It's queued to the back of the list. And that's it. Done. Does that make sense? Do you guys get the algorithm?
Yeah.
Yes.
John, glad you could join
Hello.
us.
A little late, but better late than
Little
never.
late.
A tad, just a smidgen.
Oh my gosh, it's already 2:30. What?
Oh boy, looks like you guys are going through graph theory. I haven't even reached this yet. Oh,
Yeah, you should have been on time, man.
nuts.
I'm gonna guilt trip you now.
That
Why didn't you
hurts.
come on time?
Very hurtful. Next
What
time.
were you
I gotta-
doing? What was
Oh.
more important than my session?
I may or may not have been in bed. So, I mean, pretty important, you know. Just
Facts.
you can't
Fine,
blame
fine.
me. Exactly.
That makes sense. That makes sense. All right. So, Nate, could you go back to the REPL? Now, in the interest of time, we're only going to code up depth first search today. Breadth first search will be a thing we do next time. Is that okay?
That is okay.
Good.
What would
Remember,
I say?
I
What would
always
happen if I
say-
said no, though?
No, that's not okay.
I would kick you out.
Okay, I gotcha. Then yes,
Cheating.
it's all okay.
Yes. Good. You have no option. You know, it's kind of like what the companies did. They're like, are you okay with your remote internship? If not, we'll kick you out. So
Of course.
you really have a choice. I don't think so. All right. So could you refresh the page, Nate? All right. So here's a problem that I've written. Go to the problem, please. I want a volunteer to read, only to read. Someone read this, please.
Anybody here literate?
No.
I mean,
What a coincidence. All right, as long as I don't have to do the problem, I'm fine with reading it.
all right, fine.
Beautiful.
I mean, you have to do the problem, John, but like I'll be solving it. You're just kind of like coding it with me in the sense that like
shoot.
what I meant was, well, everyone will. That's like you're kind of like what I code on screen. You're kind of like following that and like typing what I do. You know, like this is a web development tutorial, but it doesn't teach you web development. It teaches you how to be not bad.
Right. Okay.
And
Sure.
we're using Java. Just checking.
Yes.
Okay.
Yes.
Java.
I don't know any other language.
Beautiful. All right. So.
All right. Mr. Jonathan.
Okay. If I'm looking at the right thing, it says, all right, wow, you're going with the whole Arup Guha, got to write out the textbook, and then the quick little, of course, sure. So
It's inspired by him.
Right. Of course, makes sense. You should show
Okay,
this to him.
who here agrees with me? Arup is the best CS teacher.
I've never had him.
I
That's the
haven't had
thing.
I've never had him. Yeah.
Because of all the horror stories. It's been a little bit.
You know, I've had him for Intro to C, CS1, and then one more.
Intro to discrete.
No. Problem solving
dis-
and team dynamics.
Ooh,
Oh.
my buddy's taking that right now. I hear it's just leak code as a class.
No, it's not just lead code as a class.
Oh,
It's
more
lead
than
code
that.
hard as a class.
Oh, there it is. Fantastic.
okay.
Yeah.
Alright,
Remind
so
me
read it
not
out.
to take that class. Oh, right. Okay. So.
No, you should take that class. I think you
I
should.
think so. Oh, I just.
Yeah,
want the
just be
GPA.
prepared not to get an A.
Oh, I can't do that. Maybe if I secure an internship first, then I don't have to worry about GPA as much.
Okay.
But
Okay.
sure. So UCF has an internal social network. In this network, you
Let's
can have
call
several
it. Let's call it.
Oh.
Wait. Let's
Mhm.
call it UCF book. UCF-stagram.
Wow.
UCF-stagram.
Seems like
Great,
there-
great. You know, I wonder how you
fitting.
got that. You know, yeah.
no affiliation. Copyright infringement, not intended. That's fantastic. Sure. So in this network, you can have several people you're directly connected to. Those people are your friends. Then there are people who you are indirectly connected to. They're your acquaintances. Given a graph of all students in your class where an edge between two people represents their friends, and if the path from one person to another involves more than one edge, they're acquaintances, because you're such a party animal, close parentheses. So it wants you to A, print out all direct friends and acquaintances of each person, and also B, print sorted in such a way that the closest friends of each person come first. Then come the friends of friends, so close acquaintances, and then friends, and so on.
Freneds. Yes.
I call it like I see them. So,
Okay, let me fix that.
Do a little edit
Thank you,
there.
Nate.
Do-
Freneds. Yes. You guys are my Freneds.
I mean,
What an
I'm
honor.
touched. Right. So,
All right, so input format.
yeah. So the input format will be the first line will contain an integer which contains the total number of people, or n. Then there will be n subsections which start with the ID number of each person, and then numbers of friends denoted by f, which have followed. Oh, they have followed by f lines of their friends' ID numbers. And then for the output, you want to print the ID number of each person, followed by a comma separated list of people they are friends with and acquaintances with. And then you also want to print the ID number of each person, followed by a comma separated list of people in the sorted order. Gnarly.
All right, so how are we going to do this?
That's a lot. Oh. So I actually wasn't here
Ideas,
for the
bounce ideas,
part.
ideas. Give me ideas.
depth first search. We want to do a depth first search somehow.
Or
breadth first search?
I mean, there's two problems you have to solve. Today we're going to solve problem A. I don't think we have time to get to problem B.
Okay.
So for problem A, what will you do? Depth first search or breadth first search?
Depth.
Why is that?
50-50 chance. I like my odds.
Betting man, I see. Did you buy GameStop stock?
Bruh, please don't say that name around me.
Oh, don't tell me
GME
you're down.
to the moon. Just kidding. No,
I
I
work
didn't.
there.
I
Don't
didn't
even
touch it.
start with me.
Really? Oh, geez.
Yes.
Very nice.
Oh, Leia here actually works at GameStop.
No kidding. That's crazy.
Oh, proud
Whack.
owner.
Must run into quite a few interesting individuals.
No, I didn't invest.
Oh,
Like
really?
investors walking in, the door.
Probably a good idea.
Have people walk into the GameStop like, hey, I'd like to buy 17 stocks.
Yeah, I give it to you for
Cash.
350.
Yes.
I'd like to become a millionaire today.
Honestly, I can't help
Alright.
but resent that.
Problem A.
Okay, thank you for bringing us back on track, Leia. Always count on the dev team to be responsible. All right, so how are we going to solve this again? John guessed, but let's not do that here.
Right.
All right, so pretend I'm your interviewer. I'm at whatever your dream company is. And then I'm interviewing you guys. I give you this problem and I ask you to solve part A. What's going on through your head other than broccoli or something?
Panic.
We're
Right,
given a
after
graph.
panic, what do you
5
do?
times.
What do you do? What do you do after panicking?
Leave the room.
I guess you would create a graph, right? I don't know if that's made
Well,
that would
you're
sound
given
like
a
the-
graph in the sample input, but how would
okay.
you do it? Which
If you're
algorithm?
given a graph and you want to look through it, since that's what you're interested in, right? You want to go through everything.
You want a depth first,
Check it out.
Why do you think it's a depth first, Chris?
because you want to see how far for each node you can go. So basically figuring out how many friends you can get to.
You want to do depth first is the Alice one, right?
Yeah.
Yeah, step first is the Alice one.
So I guess you want to do that first because then you can backtrack back. So first it goes to yourself, then it goes to your friends, and then
Right?
it goes to
No,
the
it goes to one of your friends, then the friend of that friend, then the friend of that 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 way.
So it goes
So like you're going down the rabbit hole. Now I would like one person, someone other than John, about Leia, to read out problem statement for A again.
print the ID number of each person
That's
followed by. Wait, what?
That's not the problem. That's not the problem statement. That's the output format.
We
Could you
can't
go
actually
up?
see the.
Yeah.
Oh, there we go. Yeah.
Oh. So print out all direct friends and acquaintances of each person.
Okay. So the first thing you'll do if you see a question like that is you'll notice that order doesn't matter.
Mm-hmm.
Important. It doesn't matter what order you put the friends and acquaintances in. If it was possible, you could even print out the acquaintances first and then print out the friends. Unfortunately, that's not possible because it's not possible. So since the order doesn't matter, which one is the easier algorithm?
Depth first
With depth
search.
first.
Yes, Alice here, our very good friend Alice. So what are we gonna do?
Depth first.
Exactly. I don't know why I asked so many questions. Sometimes they may seem silly, but I'm going to pretend, as I said, that I know what I'm doing. I'm totally not nervous here. So I'm gonna live code this, but I want all of you to kind of pull up your environments and code it with me. The reason is because
Cool.
it's an involved process and it's kind of like better if you do it that way, at least for this problem. Normally I don't encourage that, but today I do. So everyone except Nathaniel, because he's our poor scapegoat. Everyone else code it up, okay? And I'm just gonna watch. No, I'm not gonna watch. I'm gonna live code. Sorry, I forgot. Okay, so what are we gonna call it? UCF Inder?
Oh,
UCF what?
like Tinder.
UCF Inder.
Oh my god.
Knight's book.
I mean, I feel like if you have it with, you could use the F twice, so you could call it UCF Finder at least.
No. It's gotta be UCF Inder. You guys know Visinder?
No. Wait, yes.
Yes. From Ben Awad.
Ben Awad. The dog.
Yeah.
What the heck?
So we're gonna kind of like copy that
Don't
guy
worry about
here. Yeah, please don't worry about that, Leah. So we're gonna import a scanner because we can't really do anything unless we get an input. All right. So at any point in the middle, I might call up on any one of you except Nathaniel to share your screen and let me see if you guys are actually doing it. Might seem a bit extreme. Yes, might seem a bit extreme, but it's really gonna benefit you guys. Trust me on that. Is that okay?
Yeah, that's fine.
Okay, great. I also get to see your open tabs. All right, so it's gonna be public class, UCF Inder. See, wrong kind of bracket. Okay, so the first thing we're gonna do is public class. Oopsie, static void in string. Even though we're not taking any arguments from the command line. All right, so next we set up scanner. Scanner name equals new scanner. This in dot in. All right. Oh, and very important, flex your coding muscles by closing the scanner right away. So this way, like they'll be like, oh, this person knows what they're doing because they want to avoid memory leaks. This must mean they've coded in C, which you guys have.
But Java does that
I
for you
think.
anyway, right? Regardless.
I know. It's just like there's
Good
this friend of
practice.
mine.
Sure.
Yeah, it's just there's this really good friend of mine, and he kind of drilled into me that I should close my scanners because he would get upset with me when I didn't.
Sure.
So I mean, the dude's an awesome programmer. So you got to respect masters of the craft, right?
Fair enough.
Yes.
Okay.
Sure.
So the first thing we're gonna do is we're gonna accept the input. Now, what I like to do is I like to take a copy of the input and just put it in comments at the bottom. This way, I actually know what I'm looking at. Because like, if you can't accept if you don't know what the input format is, you can't actually like accept input. So the first thing here is that the first thing we're gonna get is an integer which contains the number of people. So this is gonna be n. This is gonna be person P, and this is gonna be the number of friends they have. This person's a lonely boy. And then the next F lines contain the IDs of the friends they are, right? They have, and then so on. Make sense?
Mm-hmm.
So again, here's P. Like, this is good practice. This is another thing that I'm trying to drill into people here, is not just how to code, but also like how to code nicely so that you actually know what the heck you're doing. Have you guys seen those like funny Medium articles, which is like 50 lines of comments that have actually been written, and most of them are like, only at the beginning, only I and God knew how this code worked or what this code was doing.
Now only
Now
God knows.
only God knows.
That's right.
So
Oh my god.
let's not do that. So let's know what we're doing. All right. So the first thing we're going to do is we're going to accept the number of people. So standard in dot next. I hate you replit so much. Okay. So for and I equals 0, I is less than n, I plus plus. So now we have, like when. All right. Oh, the first thing we have to do once we get this number is we have to make a way of storing the graph. So I am randomly choosing adjacency matrix. Not randomly, it's just the easiest way to like store a graph. It's not very efficient, but it is pretty easy. And that's all that matters right now. An edge list is the most efficient because that's O of n storage, but an adjacency matrix is n square storage. But the good thing about adjacency matrix is that unless you're RTEing, runtime erroring, because of too much memory, which doesn't really happen too often in interviews, unless they're like, it's a HackerRank thing, you should probably store it in an adjacency matrix. It's really easy. So we're gonna do a Boolean adjacency matrix because it says nothing about like how close you are to each friend. Like maybe I'm like really close to Andrew, so that'll be represented by 1. But I'm not so close to John, so that'll be represented by 2. He's still a friend though.
Kinda hurt.
Yes, he should be hurt. He came late. Of
I only showed up 30 minutes late.
course. You chose sleep over me.
Not consciously. Just checked Discord and it was like, hey, join the Killing the Coding interview. I was like, oh, I forgot about that. But sure.
Right.
Can I ask you a quick question though?
Sure.
What's the difference between an adjacency matrix and the second thing you mentioned? Because that's the first time I've heard
You
that.
should have showed up earlier.
Ah, nuts. Right. Sure.
I actually do go over that difference. We don't have too much time.
That's okay.
That's
yeah, I'll
why,
just
but like
rewatch this.
watch the recording later.
Mm-hmm. Okay.
Yeah. So node is gonna store like the person who's like the current person. So here, so this one stores this number 3, which is the number of people. The next one shows the node. I call it P here. Actually, I should call it P here as well, for P for person. And then afterwards, we're going to store F. F is the number of friends they have. Okay. Then what we're going to do is now we have like F lines following that, which is the IDs of each of their friends. Now I could easily have adapted this question for like names instead of ID numbers, but it's just like easier for you from an algorithmic perspective to go with numbers. Later, when I do OOP, I might just come back to this question and do it using strings. Is that okay?
Okay.
Yeah, that works.
You guys don't have a choice. I chose to do it this way. All right. So here's the F lines, and we're going to store in like what the ID of the person is. Yeah. Oh, actually, no, never mind. I love you, Replit. So now, yeah, because like it actually does come with like code recommendations. It's just not as good as Eclipse or VS Code. And that's understandable because it's like a browser thing. And also like it's kind of saving my ass right now. My life right now. How to keep it PG.
Right.
So okay, so this is it. Like we've entered like taken in the input of the graph. That's it for the graph.
That
Now we
interchange
actually have to do the
node's
algorithm.
name to P.
Ah, thank you.
P.
All right. So does everyone understand what we're doing here?
Yes.
Okay.
Yeah.
Just a quick recap. It just takes your input files and puts it in the adjacency matrix.
Yes. Are you okay with that, everyone?
Yeah.
Okay. Someone else share your screen right now. Let me see how much you've typed.
I can do it if you want.
Sure.
Here.
This way, I kind
Can
of
you
want to
see
give
that?
like Nate. Yeah. I kind of want to give Nate a chance to UCF book graphs. Okay. I kind of want to get Nate. I kind of want to give Nate a chance to code as well. So Leia, could you go onto the REPL as well? The link is in the chat. This way, Nate can also kind of live code along. It's not fair for him to be like sharing his screen all the time. Thanks, Nate. Really appreciate it.
Much appreciated. I can now code.
How do I? Sure. Okay.
Well, if you don't want to do it, it's fine. Andrew can do it. I can force Andrew to do it. I always force
Am
Andrew
I in
to
the
do it.
right?
I don't have a REPL
place?
account.
Yeah, but
Yeah,
you were sharing
just
this
logged in.
last time. Oh, actually, John can do it. He was sharing last
I
time.
actually can.
Yeah, it's in the same REPL.
Oh shoot. Okay, sure.
And the link is in the chat.
Gone back to that. It's not in the chat for me because it
Okay,
needs to be reset.
I'm here, I think, so I can see if this this works. Oh my gosh, where is share?
That'll give Nate a chance to like kind of catch up to the code as well. Don't you dare copy paste, Nate.
I will. You know, I was really tempted to. I'm gonna be honest, but I decided against it. So.
Good man.
So is this good?
Can't see your screen. Are you on a Mac?
No. Oh, did I not share it?
No, it's having that glitch.
I mean, it
so.
just says started. It just says started sharing screen. John, can you do it quickly? I'll just link it again.
Yeah, can you just link it real quick and I'll.
Sorry, Leia. We just kind of on a tight schedule.
That's okay. Sorry.
Copy.
All right. And you want me to share my screen to it?
Yes, please.
Yes. Okay, screen 2.
Hey, John, after the session, could you stay up for like a little bit? I'll just explain the adjacency list.
Yeah, you bet.
Thanks.
Is it sharing the code?
I don't know. I can't see.
It is. It is long.
It is.
Do you have it like widescreen, or is it like a sliver on your screen?
I have it. It's like one of those monitors that's rotated, so it's like it's like long wise.
Gotcha.
Can you see that? Does it look funky to you guys?
It's long.
It looks fine.
Yeah. Sure. Wait, hold on. Let me see if I can share it to a different screen, and then that should do it. Share screen 2. Bam. Share. And then I'll just move this over here.
Ooh, that's super wide.
Beautiful.
That's better, yeah.
Yeah, that's good.
Sure.
Awesome. Could you go to ucfinder.java?
Yes. Okay.
Thank you.
Oh, and here I've moved mine.
Sure.
Okay, excellent. You know, honestly, UCF Finder sounds better. We're just gonna pretend that was the name from the beginning.
Sure.
Just
Okay,
like make sure I get my done. Thanks.
Huh?
Make sure I get my 5% of the company. Thank you.
Sure. So what I'm making here is a visited array. V stands for visited. This is going to be important when we do DFS, because when we go down rabbit holes, it's important to know which node we've gone to, because we don't want to keep being in an infinite loop of rabbit holes, unlike our friend Alice. Actually, even Alice escapes from her rabbit hole at some point, I think.
She wakes
So
up.
I'm going to code. Yes, I'm going to code up DFS here. And then we'll like fill out the rest of the main method. So the first thing is we're going to take in the graph, obviously. We're also going to take in the visited array. We're going to take in the node P or the person P, and we're going to call it take in the parent. Parent stands for the person who actually invited them. This is important for reasons that I will explain some other time. Well, you'll see when we finish coding up the thing.
Okay.
Okay. So first thing, if we've already visited the node, return. It's a void anyways. Aha! I didn't void it. So the reason is because we really don't want to be stuck. Like if we go to a node that's already visited, we don't want to be stuck there. So then what we do is if it hasn't exited yet, which means that this is the first time we're visiting this node, which means we mark that as visited, which is VP equals true. Does everyone understand why we're doing that?
So.
Yeah.
Okay, good. Now, if P is not equal to parent, just print it out. No, sys out. So now let's actually, it now might be a good time to look at the output format that our little program asked for, but the little problem that I wrote out. We're only going to look at A right now, and this is the output format that was requested. So the first thing you're doing is you're printing out the node itself, and then you're printing out its neighbors, or like its friends and acquaintances. Then you're printing out the node itself, then you're printing out the neighbors, and so on and so on. Now, this is the reason why I needed the parent thing in there, is because we're gonna call DFS here, and it's not gonna be visited. So if I just had a simple print out, like here, then it would print out 0 also. So 0 is his own friend, which is good. You should be your own friend. But for a social network, since it's called UCF Finder, you can't really match with yourself. No one is that narcissistic. So we need to check if, we need to just call in this little check to make sure he's not matching with himself. Make sense?
Makes sense.
Yeah, that makes sense.
And now it's going to be print because we're not printing a new line after. So it's, and then I'm just going to like print out P for the person himself. And then I'm going to print out a comma. Okay, so far so good?
Yep.
Yeah.
Yep.
Okay, so now's the real crux of the algorithm. For the purposes of people who are like the coding equivalent of grammar Nazis, we'll just do that. The graph P, even though it's like an adjacency matrix, so like the dimensions on both sides, it's a square matrix.
Did you
Let's
forget a
just keep it
semicolon
that way.
after the system out?
28.
Thank you, whoever pointed that out. From voice, I think it's Christopher.
Yeah.
Awesome. I'm good at this. Here, we're just going to call DFS again. So this is it. This is DFS. So again, if already visited, we
Okay.
return. We don't want to deal with all this stuff. Then we mark it as visited, that particular person or node. Then if it's not the same thing, we print it out. And I explained why we need to do it this way to you. There may be other ways to do it. I just didn't want to bother with that, so I found out this was the easiest. And then you just like print out, like if you just run DFS, as long as an edge exists between them. So like if there's an edge between person A and person B, then you call DFS on person B from person A. Does that make sense?
Yeah.
Yep.
Awesome. Yeah, that's it. We just need to call DFS in main now. And that's it. That's the algorithm for part A. It helps that we're kind of ahead of like over time. So I can start wrapping up here. It doesn't help actually. Contents diverged.
Oh,
I'll just
seems like
choose
there's a
my
fork.
changes.
Yeah.
That's probably from when I
Oh,
autocorrected
no.
friends, maybe.
Oh no.
Choose server changes.
Oh,
Choose my
okay, no.
changes. Server changes.
Okay, no one else type in this, please. All right, so we're just going through each person. We're gonna print out their names, so that's why like.
Okay.
Friend, we're gonna print out like the number I, which is their ID. And then we're just gonna print out a little semicolon and a space here. So that just like takes care of like this part here in the output. And I'm gonna wrap up here in a second. Then we're gonna fill array with the visited array with false. Normally we don't do this in DFS, but we have to. Like it depends on every like use case. But in this use case, since we're like we might be visiting the same node multiple times because we have to list out all the friends, we have to mark. We have to like initialize the visit array as false every time. And then DFS, we call DFS again. We're gonna call it on graph. We're gonna give it visited array. And since it's the first time we're gonna call I both times for the parent and the person. The reason for this is, again, we don't want to print this out. This will only trigger when it's the same person. And then we'll just print out a little line here just to show that there's an extra line. We're not done yet. Don't go, guys. We still have to runtime analyze this. Remember, that's kind of an important part of interviews as well. So don't go. Stay with me. All right. So can someone run this on the little terminal? Oh, there we go. I can run it.
Oh.
Oops. Someone already did.
Oh. I don't know who.
I don't know what you did.
I hit the run button, but I can't
I
actually
think
see
you
the
don't have your terminal
Yeah,
open.
you're running main. You're running main.
Oh, biscuits. Whoops.
Yeah, I'll go to shell. Oh no. Java C. Can you just go to shell or whatever?
To shell.
Yeah, shell.
Hit
Java
the
C
thing on the right.
Java.
Right.
This
The
will
little lines
compile.
below it,
The little
Oh, no.
lines. Wait.
next to the scroll bar. Sorry, like to the right,
Scroll bar. On
No,
this.
not that. No,
above.
not that.
Oh wait, I think it might be hidden by my like the zoom thing. Wait, scroll bar. Here's the scroll bar.
And then that, yeah. I think that's it. Oh no, it's
This
not.
is auto format.
Sorry, never mind.
That's fine. Just okay, here. Go like John, can you take your mouse all the way to the right?
Yes.
all the way. Yeah, you see that little like, yeah, just drag it. Like you'll see a little extend. Yeah, there we go. Not there. Yeah, bring it out.
Oh.
Yes, it's a
sick.
hidden treasure.
What the heck?
Beautiful.
The national treasure. No,
Okay, sure.
let it remain in console. Just go to console.
Oh, sure.
Okay, we're almost done, guys. Okay, so Java C UCF Finder. Java. It's gonna compile this.
Hopefully.
Whenever it's ready. The Ubuntu server is being unusually slow today.
The
There we go.
suspense.
Okay, that's also where I got an error.
Yeah, I forgot to import arrays. This is why the Control Shift or Command Shift O is useful, because it imports your libraries for you without you having to worry. This is another reason why you should use Eclipse or VS Code or whatever.
Does VS Code do that?
I don't know. Eclipse first.
Okay.
So slow.
Just a bit.
Yes, there we go. Done. Oh shit. I need to like reformat this because it'll be like, oh, what the hell is this P, F, all this stuff that you've put. This is not the format I expected. What have you done? All right, while I'm doing this, let's start thinking about the runtime for this. It's a recursive algorithm, guys. Remember that.
I see a nested for loop. Let's give it a guess. N squared.
Yay, it worked. Although it
Hooray.
prints out the extra
did it.
commas. That was expected.
Wow.
All right, does this make sense, guys? Does this
Think so.
algorithm make sense, the problem? Okay, great. So now let's
Yeah.
look at the runtime. I know I'm going way over time, but I already warned you guys that this is gonna be involved. All right, so the first thing we're doing is let's look at this.
Oh,
This is
worked.
n squared. So John, are you sharing like what I'm showing? Oh yeah,
Yeah.
that highlighted part is that's n squared. You know what? I really should switch to light mode for this. It's hard to see for me. And it's like a real like if Aileen sees this video, she's gonna laugh at me so hard. Oh yeah, Leia laughed because she knows what I'm talking about.
Her and her light mode Discord.
Excuse
Yeah.
me?
Yeah, Aileen and I
Antichrist?
often fight about it. Right.
Wild. How?
Who uses light mode for Discord?
I can't imagine it. But
Yeah.
God.
Anyway, I didn't even know light mode for Discord existed for one thing. So anyway, this is an n square algorithm.
Mhm.
I mean, this little highlighted part is n square. So that means that our problem is no faster than n square. Than this. Okay, so this is an n, like the outer for loop. And inside it, this is an n. The arrays.fill is an n O of n operation. That's another n square thing in this. But let's see what DFS is, because if that's n squared, then the whole thing is n cubed. Does that make
Ugh.
sense?
Yeah.
Yeah. Okay. So for DFS, what you're doing is you're calling an inner for loop, right?
Mhm.
And then you're just calling a DFS on that. So DFS itself is an O of n algorithm per node in this case. But since you're calling it n times, this whole thing becomes also n squared.
Oh,
So
no.
the whole algorithm's time complexity is?
N squared.
Yes. Okay, great. Does that make sense?
Yeah.
Yeah.
It does.
All right, now let's look at space complexity. We're still not done. What is the space complexity? This is an easy one. Any one of you can answer.
Order n? Question mark.
No.
It'd be n squared.
Remember how we're
Squared.
storing our graph?
Order n squared.
was
Yeah.
Yes. Okay, so that's it. That's time, space, complexity of DFS, DFS walkthrough. Tomorrow, or I'm sorry, next week, we're going to do BFS, the part B of this problem. And if time permits, we're going to do Dijkstra's. Does that sound exciting?
Just to be clear, by tomorrow you mean next week, right?
Yes, I meant next week.
Okay, just wanted to like make sure there wasn't like an early morning coding session.
Do you want to make one?
Maybe not early in the morning, no.
Will not be awake.
I mean, I don't know if I can because it's my grandparents' anniversary tomorrow. Valentine's Day.
Oh wow.
Happy anniversary.
Oh,
Lucky.
Yeah.
that's cute.
I know. So anyway, I'll be busy with that. So that's all there is to today. Thanks for coming, everyone. John, stay.
Yes, sir.